Well, thank you for the invitation. I must say, just embarrassing until it turns scary right at the end. So I should maybe start. I normally speak English quickly, so if I'm speaking too quickly, slow me down. But I put almost every word I want to say onto the screen. So that's the title. And this is what I need to say. So Jesse Douglas won one of the first two Fields medals, and what we know about him is strikingly little, actually. So yes, we know very little about him and his life, and I want to tell you what Mario Mikhailov and I have been able to discover. It's joint work with Mario Mikhailov, very much, I should say, the work of Mario at the mathematical side of this. So when it says joint work, it's slightly more than that. But anyway, Douglas was very successful at what he did, and he kind of vanished, and that's the point of the talk. This is the only picture everybody knows of him. It's the only one you will find on the web. So here we go. He was born in New York City, children of immigrants, and went to public school in New York City. He went to City College, New York, which was that time the place where a very Jewish place. And he went there at the age of 18, graduated at the age of 18, Belden Prize for Excellence in Mathematics. He then went to Columbia University for a time. He became a fellow in 1917, and he took his PhD under Edward Kastner, and that is the man who converted him to the love of differential geometry. He was an instructor at Columbia for some time, and then he became a National Research Fellow of the funded by the International Education Board, which was Rockefeller money. Rockefeller money was being spent around Europe reviving scientific life after the First World War. In 1929, he went on a tour. He went to Paris, Göttingen, where he had a bad time, Hamburg, and back to Paris. The real success he had was in Paris, and the difficulties he had on tour were in Göttingen with Courant. Courant had already had a falling out with Norbert Wiener, and Wiener was a friend of ours. And Wiener had given a talk in Göttingen, Courant in the audience, and then Courant had published very similar results very soon afterwards, and Wiener thought this was theft. It was plagiarism. The dispute went all the way up to the US consulate somewhere in Germany before everybody said, calm down, it's academic life. So naturally, Douglas is aware that Courant can be very critical and was not expecting not to enjoy it if it happened. And there are reasons to do with these degenerate parameterizations that I'll come to that he might well have been right, to be a little bit scared. Okay, he then goes to look for jobs, and Hadamard writes him a reference, and I'll let you, I think, read this. The remarkable thing about it, from my point of view, is that yes, here we are. I wanted to highlight was that he knows what to leave out, what must be left aside, and only the general development of ideas come out in full light. Naturally, I would like to do that with this talk, but there is a sting that he conveys a perfect understanding of the question, and you must tell me if I've conveyed such an understanding. So this is a very nice reference from Hadamard. And later, after Douglas has solved the Plateau problem, there's a report written about him which goes back to the IEB, the Rockefeller Foundation thing, which again, you might like to read. All mathematicians are a little crazy, says Veblen. His craziness has consisted of supporting Douglas all these years, And they think now that that's paid off. Douglas has proved to be a success. He then starts looking for permanent jobs. He gets a position at MIT. He tries to get himself to the Institute for Advanced Study, and eventually he resigns from MIT. Dirk, the differential geometer, was at MIT at the time, and he writes to the effect that Douglas kept his own timetable. He didn't turn up to give courses in the morning, and eventually, for these reasons, he had to be dismissed. Okay. This is a more interesting recommendation back for a job at Columbia in 1934. Basically, it says, excellent mathematician, you should hire him. But I direct your attention to this clause. His personal appearance is personality be around the host. Bearing in mind he had gone to City College. This is 1934 coded anti-Semitism. And it says, actually, although he's a Jew, he's okay. That's what it says. All right. So to the mathematics, the Plateau problem. There are many interpretations of it, as I'm sure many of you know. But basically, the problem consists of being given a prescribed contour, shall we say in R3, not necessarily in R3, Rn, and you want a map from the unit disk onto the inside of the contour. The boundary of the unit disk, the circle, is mapped onto the prescribed contour, and the interior of the unit disk is mapped in the right way. In the right way is to be a minimal surface, and there are many definitions, but we'll come to that. Okay. It had been much was known about this. Riemann, Weierstrass, Darboux had things to say about this, Schwarz. And what they knew was that a minimal surface, surface of least area, can always be conformally parameterized. And such a parameterization is also given by a harmonic function on the interior. Okay, so think harmonic conformal. Okay, when Douglas comes to the problem, he decides that he will take that as the definition, and he forgets, he sets aside the least area question. And Murray McAuliffe and I think that that's probably good, because at the time he would not have been able to do it, and he probably would not have accomplished what he did. So he is going to, Douglas's interpretation of the problem is to find a spanning surface of a given contour in Rn, which is given by a conformal harmonic map. Okay? And because you can always find a harmonic infill by the Poisson integral theorem, what he really wants is the right parameterization of the boundary so that the infill is also conformal. Okay? So this is the statement of problem. You always have a harmonic infill. You want a good one, G star, so that the map is also conformal. And his first way of writing this as a problem was as an integral equation for the good map. I'll define the integral equation later. I don't want to have too many formulae in the talk. So he parameterizes the boundary in a certain way. He varies the parameterization on the boundary by a homeomorphism of the boundary to itself. This will give him a new parameterization. And bear in mind, you see T's and tau's in this talk. They are creatures living on the boundary. He noticed that the integral equation he has is in fact an Euler-Lagrange equation, which is quite surprising, of a functional, and I'll show you the functional below. And it's not the one for which he is remembered if people remember him in any detail. They remember Douglas in any detail at all if he had something called the A functional. And if you look at the original paper and Douglas's explanation of it, it's impossible to imagine how he came up with it, and not at all clear why he thinks this explanation is helpful. He didn't succeed with the Plateau problem, not immediately, but he made progress, and eventually he decides that he's really onto something, he's getting somewhere. And so he writes to Veblen to say, I've succeeded in establishing its existence of solution to my integral equation in the case when the kernel K is positive for all t and tau, which is sadly not the case for the Plateau problem, but never mind. I think that I'm good. I feel good about this. The result is suggestive. And he observes that the method he has rests on regarding the integral equation as expressing the vanishing of the Volterra derivative of a certain functional. Now here's the functional, and you'll see that it contains this phi function that modifies the boundary. Okay. Now, to make this work, he appealed to Fréchet theory. So I need to step sideways for a bit and talk about Fréchet theory. Fréchet, in his thesis of 1906, had studied spaces of curves or functions, abstract spaces indeed, for which you could say certain things. You have something which looks a bit like the triangle inequality, and you can perhaps take limits. If you don't have the ability to take limits, he found there wasn't much to say, so he decided he would study those spaces, and he would also perhaps not necessarily restrict his attention to spaces that satisfied a triangle inequality. And then he found he had lots of examples of these things, spaces of functions, spaces of curves, surfaces. There's some compactness condition to make sure everything can be done. The term metric space, by the way, is due to Hausdorff, 1914, so a bit later. Fréchet had some useful topological definitions. He's very early in the game defining topological things. A set is closed if every limit point of the set belongs to the set. It's compact, we would say pre-compact, if the intersection of every nested sequence of closed sets contains at least one point. So if you're closing in on a point, it's there in your set. These kind of theorems, continuous function on a compact L space of space of limits, is bound and notate its bounds. And lower semi-continuity works when you need it, okay, which you will. So back to Douglas. Douglas becomes aware of Fréchet's theory and realizes that his functional is going to work. So this is the functional, right? This is the A functional, right? And it's obtained from the one that we briefly saw before by integrating by parts. Okay, so nothing has changed except it's integrated by parts. And then he changes the function in the kernel from g prime dot g prime. Remember, these are vectors, so that makes sense. So what you see there. And because it's integrated by parts, there's no need to differentiate anymore. Things merely have to be continuous, right? It took Douglas a year to spot this little trick, by the way. That's the 29 to 30 period of what's going on. But now, unlike what was before, when you had functions that were differentiated before they entered into the integral, nothing is. The phi has disappeared. And so he thinks his functional has several advantages over the functionals that were available, like the Dirichlet functional, it manifestly bounded below, and it extends to what are called improper parameterizations. He's now parameterizing the boundary of the contour. So here's a contour, and here's the unit circle. You have a little map, and he's parameterizing gamma, right? And he thinks of this as defined by a graph. There you have C along here, gamma along here. You need your parameterization to be monotone. It must always be going around in the same direction. Okay? And ideally, you want it to be strictly monotone. It's always increasing. Okay, so what you want to have the parameterization which looks something like that. Starts here, finishes there, right? Goes all the way around, goes all the way around. The things you don't want, I'll go one or two examples. You don't really want this transfer for a bit, because this will not give you a good spanning distance. But what you really don't want, well, that's Courant proper, is a two kinds of proper, that's not what you do. What you don't want is that. And when you've got limiting arguments about a whole family of parameterization, right? You don't want to discover you've got this one out of a limit of things like that. There's one of them. Here's another one of them. So you think of this endpoint moving that way. This endpoint as moving that way. And this one moving faster than that. So in the limit, the top one and the bottom one more or less coincide, okay? And you get the graph like the bar, like the curve. Limiting function takes two values. One function everywhere except at one point. One value everywhere except at one point. This is what you really have to avoid, okay? So, what he noticed was that, first of all, you could eliminate this business with G's and G primes. And then to avoid improper parameterizations, what it seems to call difficulties, you can always transform the map you're using by a Möbius transformation. A Möbius transformation will take any 3 points on this circle to any 3 points here you like to specify in advance. And it turns out not to alter the value of the A functional. So because you've got this capacity to say that at least it takes 3 points to 3 points, you should be able to, with a bit of argument, try to suppress, eliminate most of these difficult parameterizations. So what did he do? He takes this space of strictly monochrome parameterization. They are the good ones. They will give you nice spanning surfaces. He compactifies this space, and as so often when you compactify a space of good things, in come the difficult ones on the boundary of that space. Okay, the improper and the degenerate representations of like that. These he called representations of the boundary curve on disk. The A functional is defined on the original space and can be extended to a bigger space, but not a closed subspace of the space which contains all of the improper and degenerate ones. However, the Möbius transformations come to your aid and they allow you to reduce the space you're talking about to a space which is closed and in which limits exist. The A functional is lower semi-continuous everywhere on this thing, and the problems of improper and a bit more work degenerate parameterizations go away. Fine. To sum up, he has an integral equation. It's the Euler-Lagrange equation of a functional called the A functional, defined on the space of parameterization. By Frechet theory, this functional attains its minimum, its Frechet derivative vanishes, and for that parameterization, the harmonic infill is also conformal, and he's done the job he set out to do. Accordingly, he writes his first big paper, 1931, and he describes the A functional, something to do with chords on a circle. He observes directly that the harmonic extension of a minimizer of the A functional is conformal without any reference to the integral equation. This is not a well-written paper, although others could be very clear. He does this last task of establishing that things are conformal by taking the Fourier coefficients of the background boundary and varying them and checking on what happens. And in this way, he gets the conformal harmonic spanning surface. Okay, so not so much use of the A functional and its properties as you might think, given his route towards it. But at all events, it works, and it works for any Jordan contour in space. Right? No requirements that the Jordan contour be, for instance, rectifiable. He also notices, he's the first to notice, that this argument works when n is equal to 2, when your contour is a Jordan curve in the plane. And in that case, you get the Riemann-Osgood-Caratteidori theorem for free. The Riemann theorem says that if you have a map, if you have the disk, the interior, the disk, and a contour, you can map the disk, not necessarily the boundary, but you can map the disk conformally onto the interior of the contour. The Osgood-Caratteidori addition to that theorem says that this map extends to a continuous map on the boundary. So your conformal infill extends to a whole map of the boundary. And you get all of this for free from Douglas's theorem. So this is the first time anybody's noticed that the Plateau problem works when n is equal to 2. He also has success with problems where any spanning surface would have infinite area, and he gives examples. Okay, very, very crinkly curves. Okay, not so difficult to define them, but very difficult to draw. Spanned, but only by surfaces of infinite area. But what happens is that if you take curves on the interior of a spanning surface, they have finite area, and they are conformal harmonic infills, okay? And then you can let them grow out towards the boundary. And what he said was really all of infinity lies on the boundaries, okay? So he can define what it is for the Plateau problem to make sense, even though the area of the spanning surface is in fact infinite, by a limiting argument. And the first time, again, that any result like this had been obtained. The idea that there were curved spanning surfaces, the idea that there were boundary curves, all of whose spanning surfaces were infinite, had never been considered before. Douglas shows that they exist and his methods can handle that. He then went on to notice that you can do this with non-orientable surfaces like the Möbius band. His argument extends, not completely easily, but it does extend, to Möbius bands and to surfaces with two contours, such as the famous catenoid. Any two contours, if they can be spanned at all by one connected surface. And for this, you've got two boundary curves for the spanning surface to span. That spanning surface will be an annulus. It will have a modulus to do with its conformal structure. And so you have to make sure that the maps you are getting from the Douglas process are also respectful of the modulus. And he was able to do this. Okay, so this is how the shape and the position of the two boundary curves comes in, introduces a modulus into the question, and his methods can work for that. So now we come to the bit he left out. As I said at the start, the Weierstrass-Enneper equations back in the 1860s enabled it to do a lot. And without the modern precision about what minimal surfaces are precisely, he wants, what Douglas has is conformal harmonic infill of a given contour. He wants to prove it has least area. And this he can't actually succeed in doing, or at least he didn't succeed in doing. It would be possible to do such a theorem if he knew that every surface can be conformally parameterized, but that's not proven at the time. The Korn-Lichtenstein theorem, 1916, does this only for surfaces immersed in R3. So more complicated looking things that aren't immersed, there was not the machinery to deal with. It was not known a priori that an area minimizing surface is necessarily immersed. So Douglas' argument stops at this point. It's not an argument about area minimizing surfaces. Okay, I promised you the rival, Tibor Radó, and here he comes. Radó has an interesting life, actually. He studied technical engineering, civil engineering in Budapest. He joined the Hungarian army, the First World War. He fought behind the lines. He was captured. After the Russian Revolution, prisoners were shipped off to Siberia, which is the hazardous journey, 4,000 miles east. And there he was put to work in the railway yards. And he escaped with a group of prisoners, rather wonderfully. They hijacked a train, okay? This is not your ordinary kind of walking out, hidden in the laundry basket. They stole a train, okay? And they got away with it. They got rescued by an American finance boat that took them as part of the reparations for the First World War. In 1920, he was back in Europe, back in Hungary. He studied with Alfred Haar, Friedrich Ries, with whom he did his PhD. He spent some time in Szeged. He gets the Rockefeller Foundation that enables him to go to Munich with Caratiadori and to Leipzig with Kerber and Liechtenstein. These are some of the big names at the time in complex function theory. So he's embedded in this milieu. These are the people that he learns from. Okay? And in 1929, he goes to Harvard, possibly inspired by a very successful visit that Caratiadori had. And might well have said to him, but we don't have the letters, that you should go there. And in 1930, he decides to stay in America. He becomes a full professor at Ohio State, and he stays there until his retirement many years later. So again, what's a minimal surface for Radó? You have a simple closed curve, and you want a map which has as its harmonic infill a conformal map and the appropriate boundary. And now, instead of the Douglas approach, he uses some of Kerber's theorems on uniformization, specifically this one. If you have a polyhedral surface, it can be conformally parameterized away from the vertices. Okay, something funny happens at the vertices. And look at a regular solid. Okay, the angles of a regular solid are not going to be 2 pi. Okay, so he now has a very neat argument. Okay, consider a polyhedral spanning surface first of all. It will have a minimum area spanning surface, and you will choose a polyhedral spanning surface, which is very close. That will give you, using Kerber's theorem, another surface, using Kerber's theorem, will give you a conformal parameterization of the polyhedral surface. This gives you a parameterization of the boundary, and now you use the Poisson integral formula to get yourself a harmonic surface. So you've now got a polyhedral surface and a harmonic surface with the same polygonal boundaries. And the area of the harmonic surface, this is the lemma he proves, is less than the area of the polyhedral surface. So now if you let epsilon tend to 0, you will succeed in getting a harmonic conformal surface. In a little more detail, okay, your polyhedral surface, big pi epsilon, this guy is within epsilon of the least you can do. You can give it a conformal parameterization or isothermal parameterization, which satisfies this. E is equal to G, F is equal to 0. You restrict it to the boundary of the unit circle. You get a harmonic thing, the harmonic extension of the restricted map, and it's be a harmonic surface. So I sort of thinking it was being a nicer fit, this polyhedral boundary, than the other one. And then you prove there's a better, even better polyhedral surface. And you go from the polyhedral surface to the harmonic surface to the polyhedral surface and back. And in this way, you will succeed in getting a surface of a limit, which is a conformal harmonic infill of your polyhedral surface. That's what's wanted. Okay? It works because of that area inequality which I showed you before, which shows surfaces as the comparison of the Dirichlet energies of this. And the meat of the proof was this little chain of inequalities. Okay? The first one is just what A inf is. The next one is what the polyhedral surface is. It's conformal, so you can do that to it. The Richelieu estimates give you the next one. That one is standard differential geometry, and now you're through to the end, and you just take a psilon to be sufficiently small, and you've got your harmonic conformal surface spanned by your given boundary, and you've won. This is pretty nice. Okay, it's standard. Well, it's a very clever use of conformal mapping, standard differential geometry, what I might say was kind of European style, and it's certainly more intuitive than Douglas's. Okay, what about an arbitrary contour? At least, how about a rectifiable contour? Radó also has an argument which says that you can take your polyhedral surface and the polyhedral boundary and push your polyhedral boundary out towards the given one, which is rectifiable, taking a minimal surface with it. This is not obvious. We have to prove it, but it's true. Okay, so from his previous result and the fact that you can take a polyhedral curve sitting inside your rectifiable one in some sense, and just push it out and it will bring the minimal surface with it, he has shown that rectifiable surfaces always have minimal surfaces on the definition of being conformal harmonic. Okay, and so this is the Plateau problem for disks in R3 with rectifiable boundaries. We don't know for sure, but we suspect that the first time Radó heard of Douglas was when he was in Harvard. And I would love to know how. The most likely thing we have is it might well have been Birkhoff Sr. We don't think that Douglas was back in Harvard at the time. Okay? When challenged about this, Radó says, well, my proof works for area. Douglas doesn't work for area. And Douglas replies, I'll do that. I can do that. And he never manages to do it. Okay? So he has to fall back on Kerber's uniformization theorem, just as Radó had done, in order to get least area among the spanning disks. So now Radó goes on to the attack and says that his proof of this Plateau problem is simpler. And Douglas had used Kerber's theorem anyway, so, what's the big deal? And that the existence of a minimizer for the A function is easy to establish, even without seeing the solution of the Plateau problem. And Mario and I don't think that's really fair. It wasn't easy. It isn't easy. This is Radó pushing his luck a bit. A little later, 1931, he goes back to this and essentially says, okay, look, supposing what we do is work with the whole disk rather than just boundary curves. And this opens the way, that's all I want to say about this, opens the way to what Courant was to do a bit later, when Courant emigrates to New York. And this is the end of the A functional as a gadget. Okay? Courant's work, more or less, because it's better for more complicated surfaces, higher topological types and things like that, it removes from the study of minimal surfaces Douglas's A function. And it's one of the reasons why Douglas is less well known. Okay. So Douglas responds, of course, to all of this. He gives simpler proofs using Kerber's uniformization. And he claims that, well, really, the Plateau problem and Kerber's uniformization theorem are about equally difficult. So all Radó has done, is to establish that the Plateau problem is a corollary of the Kerber theorem, right? So this is kind of playing down what Radó had done by saying, yeah, you're halfway up the mountain already, and you just finished climbing. I don't think that's fair either. I think Radó's original argument is really quite attractive and quite simple. Anyway, we come to the Fields medal. This is a picture of the actual one. If you look carefully, it says Jesse Douglas a bit below, because Mario knows Jesse Douglas's son, Lou Douglas, and that's where we got it. Lou Douglas still has the medal. So what is going on behind the scenes for the Fields Medal thing? Douglas had traveled, as I said, to 1929. He had a bad time in Göttingen, thanks, we think, to Courant. But in 1931, he gets a very positive letter from Courant. I mean, the big paper is out, and Courant writes and says, "We're very pleased that you've done it." Hammond Weil includes Douglas's results in one of his lecture courses, and that's good. Why they chose Douglas and not Radó, we can't find out. There are no records of the Fields Committee minutes or anything that might have shed light on this. It's true that Douglas is younger than 40, Radó is just over, and that may be the origin of the story that you have to get your Fields Medal before you're 40. It wasn't a factor here. We simply don't know what was the reason. No evidence that we can find. But what really, in a way, surprising and a little shocking is what Tibor actually says in the reported proceedings. He praises Douglas for his originality, much less use of existing theory, greater significance, and then sketches an approach to the problem, which is essentially Radó's. Now remember, Tibor and Radó knew each other very well. So he gives what is essentially Radó's approach to the Plateau problem, whilst praising, in the speech it is supposed to praise Douglas. Okay? He then remarks that Douglas had solved the Plateau problem, even when the spanning surfaces must have infinite area, only to remark that that's not really the Plateau problem, is it? I mean, the Plateau problem is about minimal area. And so he adds and he subtracts. He goes to Radó when he could have gone to Douglas. And he praises the great generality of, never mentions that you get the Riemann-Osgood-Caratteidori theorem for free, which is a very nice corollary to have. Okay, so that's what Caratteidori says. Briefly on Douglas's later work, he extends it to arbitrary topological types, arbitrary many boundaries spanned by a surface of prescribed genus, before Teichmüller theory. So very little chance of real success. He uses the theory of theta functions to handle the moduli that turn up, and Mario tells me that the calculations are very difficult and have probably never been fully checked. And even so, it's a viable program for solving a Plateau problem at the most completely general level, and for that, undoubtedly deserves credit. What happens to Douglas in later life? Well, this is why he's not so well known. Between 1936 and 1938, he seems to have had a nervous breakdown. So, for example, Veblen writes to Flexner, who you know is in charge of the Institute for Advanced Study, that Douglas was at MIT, but a couple of years ago he had to stop his work because of a nervous breakdown. He's been on leave of absence at home in Brooklyn, and now he's back. I'm very pleased to see him in a good state of health. On his return, he visits the Institute in 1938-39 as the status of official visitor. He's hoping to get a job, but by this time, there are people coming from abroad fleeing the Nazis, fleeing Mussolini's fascism, and the position he hoped to get, I think, goes to Fubini. And okay, he's completely recovered. What's he going to do? He goes to Columbia. He works on problems to do with gas masks. He hopes to be hired at Columbia. And Marston Morse, very distinguished mathematician, as you know, is writing letters on his behalf. He goes to Brooklyn College, where he teaches for a time. He's well regarded for his war teaching. He gets a distinguished medal from Brooklyn College. He gets he gets awarded these medals from the American Mathematical Society. And meets Jessie, Jessie, his wife, and they get married. They have a son, Lou. Douglas was born in 1944. They get divorced in 1950, and Jessie, unfortunately, was killed in a road accident in 1957. In 1946, Douglas is elected a Fellow of the National Academy of Sciences. And from there to 1950, his record is absolutely blank. You can't find anything. In 1961, he teaches the general studies, and he becomes a lecturer at Columbia. And he also teaches mathematics at Yeshiva, which is a Jewish seminary, for a couple of years. He got a course in modern algebra there. And he gets recommendations from people saying if it's really wrong that he doesn't have a college position, something must be done. And so clearly his problems with his mental health are getting in the way of him being hired, and he does what he can after the 1950s. Marston Morse again writing to say, look, to Bennington, it's back at City College, okay? The Peas are going to hire him, and would want to hire him. It's disappointing that he has not been hired. Frankly, the world outside will wonder and think the less of you than it will think of Douglas. You really should have hired this man. Okay? And he does seem to have been remembered quite warmly by people who knew him. Norman Schaumburg, who writes a little article about him in the Dictionary of Scientific Biography, says that Douglas could be a good teacher when he chose, and he liked to get up late. Presumably he did at MIT. And so he often thought the elementary assigned classes, which were held in the evening, it's a neat solution to the problem, right? But I think also it connects with his depression. He wasn't so good at getting up at all in the winter months. And he also harbored dislikes of his life, not only of Radó, but even of J.F. Rich at Columbia. I don't know why. And he could be rather unkind. One student asked him what he had to do to get an A grade, and Douglas said, get better parents. You can't do that now. Okay, let me say, you can't say now, get better parents to your students, all right? On the other hand, students went to complain about another teacher, and they got the reply from the head of the department, look, we've got a very person who complained about a very distinguished mathematician, we ought to be very happy to have him. And the student said, no, we don't want someone like that. They said, we want a real mathematician, someone like Douglas. Okay, so he liked teaching. One of his lines was that proving a theorem is like negotiating a bargain. Right? The tougher the conditions, the better the bargain. Right? You get more results out of a harder theorem, as it were, negotiating harder to get it. 1965, he takes leave, and in 1965 he dies, and the question arises of who should write his obituary. The suggestion is Courant. No surprise there. Courant declined. In fact, Eilenberg was astonished that Courant was passed. And Louis and Murray declined, and they write again to Courant, who said, yeah, okay, I'll try and do it, but I can't promise anything. And he didn't deliver anything. Okay, make what you like of that. As I say, Courant was amazed that they'd even approach him. This is the new photograph. The only one we have is not very clear. Hardly clear at all. It comes from Louvre as a picture of Douglas, and that's all I have to say about it. So, thank you for listening.
Thank you, Jeremy. Thank you very much for your nice, interesting talk. Any questions? Who was part of the committee which gave the tips?
Oh, that's a good question. Courant is the only one I can. No, sorry, not Courant. Carpiadori. I can look it up and ask me again afterwards, and I'll look in the long book version of that. I think possibly Burkhoff. Yeah, but that's a speculation. Yes.
But they never say it was up to them why did they choose?
No, all we have is the speech that Carpiadori gives. That's it. There's no kind of letters between them or correspondence. If there ever was, I don't really know how they did it. Maybe they just said, okay, you better write it. You know these guys. So that's the story there.
Okay. Any other questions?
So there is a reason why in 1929 that was coming to you? There is some international congress.
Yes, I think there is a reason.
The result presented maybe
Yes, yeah.
1980,
I think
28, 29.
yes, I think there is a reason. And that reason is that Americans still think that it's good to get a European reputation. The first person to do this was Birkhoff with his solution to Poincaré's last theorem, right, in 1913. Okay, this is the first time when Americans impressed Europeans, really impressed them. And I think that this is quite likely that Veblen, who is very much of an Anglophile, and Birkhoff, who knew that his reputation had been boosted by the fact that this European reputation, said, look, why don't you go and talk to these people? You know, you can give talks, you're good at it, and, you know, it will establish you as a major mathematician.
Understand.
Okay, I think it's to do with reputation. Okay, fame. You have to be noticed by Europeans. After the Second World War, it was the opposite. People went to America in order to say, you know, I've had a position in Harvard, and then they would come back to Europe. But in this period, you go to Europe. So I think that's the answer. And Göttingen is, well, Hilbert is there. Klein died recently. It's still the place. It's a terrifying place, right? I mean, you have to imagine a front row of half the mathematicians you can name today there, okay, waiting for your first mistake, the first chance to cut your proof down by half. You know, all of these people. So yeah, but that I think is the reason. Okay.
I thought this would be like, well, no,
Yes. Yeah.